solve today. It is the drag force on a train surface. So you can see the schematic here. So the top surface of the passenger car of a train moving at the velocity is 95 km per hour. This is the dimensions of the train. You can see 2.1 meter wide, 8 meter long. So the outdoor air pressure and the temperature is given. We need to calculate the drag force acting on the top surface of the car. And we need to just ignore the off-stream boundary layer, and so we're not going to actually consider the boundary layer effects for this problem. So what we need to do is we need to calculate the drag force, okay, acting on the top surface of the car. So we'll write down some assumptions at first. So for this problem, the assumptions are just as usual. We will say this is a steady and incompressible flow. Okay, this is steady and incompressible flow. So this is our first assumptions. In this case, we assume that the critical Reynolds number is 5 and 10 to the power 5. Okay, so this is our assumptions. Let's assume that the critical Reynolds number, say our critical Reynolds number 5 and 10 to the power 5. Okay, maybe you just ignore this one. We say this is ideal gas problem. So air is ideal gas. Okay, and we are going to calculate the drag force on the top surface of the train. So we'll say that the top surface, this is a smooth surface, but the reality could be different. Yeah, but in this case we said the top surface is smooth. The top surface, this is smooth. So that's all of our assumptions. Now we will calculate some properties. Like we assume that the critical Reynolds number is 5 and 10 to the power 5, but we don't know. So let's say the property is at 1 atm and 25 degrees centigrade temperature. So we can write it down. Okay, the density from the table, it is 1.184. This is kg meter cube, and the kinematic viscosity is 1.562 and 10 to the power minus 5 meter square per second. So this is the value we got. Yeah, so now if we calculate the Reynolds number to see whether the flow is laminar or turbulent, so let's calculate the Reynolds number. If you ask me that why you are calculating the Reynolds number, look, we need the drag force. Okay, we know the drag force, it is equal, in this case it is the drag coefficient. It will be all about the friction coefficients. So we can say CF, the area A, rho V square over 2. So that means we need CF, and CF, it is related to the Reynolds number. Okay, so then we need to check the Reynolds number. So let's calculate the Reynolds number at first. So here Reynolds number, the velocity, length, kinematic viscosity, or if you use the dynamic viscosity, then you need the density. So in this case we actually don't need the density. So the velocity is 95 km per hour, so we can say 95 into 1000 over 3600, that is meter per second, into length. For this train, it is if you see, it is 8 meter long. So 8 meter over the viscosity is 1.562 10 to the power minus 5. So we'll get this Reynolds number is 1.352 10 to the power 7. So this is greater than this critical Reynolds number. So flow is turbulent. So you all know this. So now the flow is turbulent. So as it is greater than the critical Reynolds number, so we will actually consider the combined effect of the laminar and the turbulent flow when we will calculate the friction coefficients. So we already know the friction coefficients for this both effects 0.074 over the Reynolds number, power 1 by 5, and this is 1742, and the Reynolds number. So this is the the friction coefficient formula we know for the combined effect of the laminar and the turbulent flow. So in this case, let's substitute the value. This is 0.074. The Reynolds number is 1.352, and 10 to the power 7. This is 1 over 5 minus, it is 1742, and the Reynolds number is 1.352, 10 to the power 7. So we'll get it is 0.002645. This is CF. So once we have these friction coefficients, then in this case, if you see, we only considering the friction coefficient, that means the pressure drag here is 0, because you already know the flow is actually how the flow is actually working. Pressure actually acts this way. So here the angle is theta equal 90 degrees, so we can cancel out the pressure drag. So we can say that means the CF, CD, this is same thing. CD equals CF, okay? It's just a combined effect of the friction and the pressure drags, but pressure drag is 0. So we can say this is equal to CD. Or it's kind of a flat plate here, okay? Yeah. So we can just write it down here. The FD, this is equal CF A rho V square over 2. CF equal 0.002645. The area, it is we know the dimensions, 8 into 2.1. So this will be the area, and the density. Now we need the density here, 1.184 into the velocity square. So we know the velocity is 95. So I will just make it simple, like 95 over 3.6. Okay, this is a square, and this over 2, and we need to just convert it into like 1 Newton equal 1 kg meter per second square. So if we simplify this, then we'll get the value is 18.3 Newton. So this is the drag force that we need actually. Yeah, so if you want, then you can solve. Here you see I used the combined effect of the laminar and the turbulent flow, but you can solve it only for the turbulent flow, okay? And that will not deviates the final value. Yeah, it will be more or less kind of closer, because we have got the Reynolds number is just greater than the critical value. So if you want, then you can use only the turbulent flow equations for this drag coefficients, but here I actually used the combined effect, okay? Yeah, so and this is just little bit far from the reality, because in this case we consider this the smooth surface, but in reality it is not smooth. It could be rough surface, okay? So then we may get much greater value here. Yeah. Alright, so I think this is the solution, and I believe you understand this.